Hello students, welcome to EPG Pathshala. I am Reema Gupta from University of Delhi and today we are going to discuss about the module that is Defect Chemistry Part 3 and this is from the paper Ceramics. So students, let us see what we are going to learn in this module. So we will be discussing about defect equilibriums in stoichiometric oxides and the same procedure, that is defect equilibria in non-stoichiometric oxides. So let us talk about the defect equilibria in stoichiometric oxides. So the defect which is we equally consider in stoichiometric oxides are Schottky and Frenkel defects. And the following slides will help us to analyze both the defects and their types and their behavior. So students, let us discuss about defects equilibria in stoichiometric oxides. The defects which we usually consider in stoichiometric oxides are categorized into two main categories. The first is Schottky defect and the second is Frenkel defect. So first we will be discussing about Schottky defects for an oxide, that is MO. Here M is corresponding to any metal and O is corresponding to oxide. So let us discuss about the Schottky defects. So the defect reaction for an oxide MO can be written as 0 or null gives VO double dot plus VM double prime. The equilibrium constant for this reaction is Ks, which is equal to VO double dot into Vm double prime, that is the products of the reaction. The equilibrium constant is Ks. So here square brackets, that is 2 square close and opening brackets, are used for the concentrations. So equilibrium constants are the multiplication of concentration of the products, that is VO double dot into Vm double prime. Equilibrium constant can also be expressed as Ks is equal to exponential times minus delta Gs by RT, which comes out to be K naught exponential of minus delta Hs by RT, where delta Gs is the molar free energy of defect formation and is delta H minus T delta S, and here delta H is the enthalpy for defect formation, delta S is the entropy change, which is mainly vibrational in nature and can be assumed to be constant. That's why the contribution from S, that is entropy, has been neglected and Ks is represented as K naught exponential of minus delta H by RT. So this leads to the expression K naught exponential delta H by RT. So if Schottky defects dominate, then VO double dot, that is concentration of VO double dot, is equal to concentration of Vm double prime, which is equal to Ks to power 1 by 2, which comes out to be K naught to power 1 by 2 exponential times minus delta Hs by 2 RT. Here one can see that the defect concentration are independent of oxygen. So the next defect which we are discussing is Frenkel defect. For an oxide MO, the reaction is MM gives Mi double dot plus Vm double prime, which leads to Kf is equal to concentrations of Mi double dot and Vm double prime divided by Mm concentrations, that is the products by reactants. or it can be written as Kf times mm concentration is equal to concentration of Mi double dot and Vm double prime. At reasonably low defect concentration, when Mi double dot and Vm double prime is very much less than mm, then mm is approximately 1. Then the equation becomes Mi double dot into Vm double prime concentrations are equal to Kf. If Frankel defects dominate, then Mi double dot is equal to Vm double prime. That is, Mi double dot is a Vm double prime, which comes out to be Kf to power 1 by 2. In a similar manner, what we did above for Schottky defects, we can now write the expression, that is, concentration of Mi double dot is equal to concentration of Vm double prime, which comes out to be K naught to power 1 by 2 exponential minus delta HF by 2 RT. Again, we can see that the defect concentration is independent of O2. Now we talk about defect equilibria in non-stoichiometric oxides. So the first case is oxygen deficient oxides. So in present case, we are considering the oxide that is MO type oxygen deficient oxides. So the condition for it is either oxygen vacancies may dominate or the metal excess may dominate in the form of metal interstitials, or even both kinds of defects are simultaneously present. Case 1, when oxygen vacancies are dominant defects. Case 2, which we will be discussing, is when metal interstitials or metal excess dominates, and the third case is when both kinds of defects are present. So the first case was when oxygen vacancies are dominant defects. Here, the defect reaction can be expressed as OO gives VO double dot plus half of O2 plus 2 electrons. The reaction constant will be K is equal to VO double dot times Ne square times PO to power 1 by 2. Here, we assume that the concentration of OO is 1. From the above reaction, to maintain the electrical neutrality, Ne is equal to twice of VO double dot. Thus, the reaction constant becomes K is equal to 4 times V naught double dot to power 3 into PO2 to power 1 by 2. Or we can write as K is equal to 1 by 2 NeQ PO2 to power 1 by 2. So from this expression we can calculate Ne, and Ne come out to be Ne is equal to 2K times PO2, where 2K is to power 1 by 3 and PO2 to power minus 1 by 6. And V naught double dot is equal to 1 by 2 Ne. So the relation between the defect concentration and PO2 can be seen in the schematic figure, which we will discuss in the next slide. So students, you can see the schematic where defect concentration are varying as a function of PO2 to power 1 by 6. This makes sense because the concentration of vacancies will go down as we supply more and more oxygen to the material. Now comes case 2, that is, if interstitial metal or metal excess is present. Here, the defect reaction will be MM plus OO gives Mi double dot plus 1 by 2 O2 plus 2 electrons. So the equilibrium constant can be written as Kx is equal to concentration of Mi double dot PO2 to power 1 by 2 and N times E square divided by concentration of MM and OO. Here, both MM and OO can be assumed to be 1, and if the concentration of Mi double dot is very much less than the concentration of MM and OO, then according to the electrical neutrality condition, the Ne is equal to twice of Mi double dot. Thus, 1 by 2K is equal to Ne cube PO2 to power 1 by 2, or Ne is equal to 1 by 2K to power 1 by 3 and PO2 to power minus 1 by 6. So this plot which we obtain from this expression is very much similar to the above case, that is case 1. Case 3 is simultaneous presence of oxygen vacancies and metal interstitials. Such a scenario is found often in ceramic oxides like titanium oxide, that is TiO2, and niobium oxide, that is Nb2O5. Consider a metal oxide, that is MO2, with doubly charged oxygen vacancies and metal ion interstitials. The corresponding defect reaction is OO gives VO double dot plus 2 electron plus half O2, or MM plus 2O gives Mi double dot plus 2 electron plus O2. Assuming that the concentration of OO and MM is approximately 1, so the defect equilibrium can be written as the concentration of VO double dot times Ne square, PO2 to power 1 by 2 is K1 and K2 is equal to concentration of Mi double dot Ne square PO2. So according to the electrical neutrality condition, Ne is equal to twice of VO plus twice of Mi double dot. Two limiting conditions are: the first is when concentration of VO double dot is much greater than Mi double dot. So the equation becomes half of Ne is equal to concentration of VO double dot, which is equal to K1 by 4 to power 1 by 3 and PO2 to power minus 1 by 6. And Mi double dot is equal to K2 divided by Ne square times PO2, which comes out to be K2 divided by 4 into K1 by 4 to power 2 by 3, PO2 to power minus 2 by 6 into PO2. That is, the concentration of Mi double dot is equal to K2 divided by 2K1 to power 2 by 3 times PO2 to power minus 2 by 3. As you can see, under such conditions, the concentration of Mi double dot increase more rapidly with increasing PO2. This is commonly observed in titanium oxides and niobium oxides, where VO double dot concentration can be 10 to power 10 times higher than that of the concentration of Mi. So the second limiting condition is when the concentration of Mi double dot is much greater than VO double dot. So the following similar exercise as above, as in the previous slide, we can calculate that the concentration of Mi double dot is equal to half of Ne, which comes out to be V2 by 4 to power 1 by 3 times PO2 to power minus 1 by 3, and VO double dot is equal to K1 by 2K2 to power 2 by 3 times PO2 to power 1 by 6. Here, the concentration of VO double dot increases with increasing PO2, while keep decreasing with increasing PO2 but at a different rate. Now comes metal deficient oxides. So the metal oxide, that is MO oxide, with complete ionization of vacancies for the reaction, half O2 gives OO plus Vm double prime plus 2 holes. So for this reaction, the reaction constant is the concentration of OO into concentration of Vm double bar into NH square, that is whole concentration, divided by PO2 to power 1 by 2. So if we assume that the concentration of OO is 1 and the concentration of Vm double prime is very less than the concentration of OO, then the reaction constant will be equal to Vm double prime concentration into NH square into the partial pressure of oxygen. So for the electrical neutrality condition, the whole concentration, that is NH, is equal to twice of the concentration of Vm double prime. So in this case, half of Ne will be equal to Vm double prime. Why? We know that NH is equal to Ne, so we are replacing it and saying that half Ne is equal to Vm double prime concentration. So this is in turn equal to K by 4 to power 1 by 3 into the partial pressure of oxygen, that is PO2, to power 1 by 6. So the further analysis is left to you to perform themselves and assume that the intrinsic ionization has dominant defect in stoichiometric conditions. So students, let us summarize what we have learned in this module. So in this lecture, we have learned that the defect equilibrium for defect reactions. So we have read this case for both stoichiometric and non-stoichiometric oxides. So in stoichiometric oxides, we discussed that the defect concentration is independent of partial pressure of oxygen, while there is a strong dependence is there in case of non-stoichiometric conditions. So the nature of dependence is always governed by the nature of defects present in it. So by writing appropriate defect reactions and considering limiting conditions, one can determine the dependence of defect concentration on partial oxygen pressure. Now comes metal deficient oxides. Now we turn towards the case of metal oxide type oxides with deficiency of metal, which can be reflected either by metal vacancies or oxygen interstitials, or we can say the presence of both metal vacancies and oxygen interstitials. Here we do analysis only for the metal vacancies, while other two cases can be done in a similar fashion as we are doing the first case. So for metal oxides, assuming complete ionization of vacancies, we can write the reaction as half of O2 gives OO plus Vm double prime plus 2 holes, whose equilibrium constant can be written as K is equal to concentration of OO and Vm double prime times NH square divided by PO2 to power 1 by 2. If the concentration of OO is 1, then the concentration of Vm double prime is very much less than the concentration of OO. Then the equation becomes K is equal to the concentration of Vm double prime NH square times PO2 to power 1 by 2. So according to electrical neutrality condition, NH is equal to twice of the concentration of Vm double prime, and hence half of Ne is equal to the concentration of Vm double prime, which comes out to be K by 4 to power 1 by 3 times PO2 to power 1 by 6. Again, the concentration of defects is proportional to PO2 to power 1 by 6. So one can do similar exercise for the cases when oxygen interstitial is the main defect and also when there is mixed presence of metal vacancies and oxygen interstitials. This is left to you, to the students, to perform themselves. So using the limiting conditions, in the module we have discussed that there are two limiting conditions. So the first limiting condition which we have discussed was when VO double dot is greater than MI double dot. So in this case, we have written the reaction rate and find the reaction constant. And we have discussed that under such conditions, the Mi double dot increase more rapidly with increasing partial pressure of oxygen. And commonly observed examples for this case is titanium dioxide, that is TiO2, and the another example for this condition was niobium oxide. The niobium oxide is Nb2O5, where VO double dot can be of 10 to power 10 times higher than Mi. So the second condition which we have discussed is where Mi is much greater than VO, means metal interstitials are more present. So the similar analysis as of limiting condition 1 was carried in this module, and we have found that the VO concentration increases with increasing partial pressure of oxygen while keep decreasing with increasing partial pressure of oxygen but at a different rate. So we can conclude that the VO concentration first increases and then decreases afterwards. So students, now you are able to understand the defect equilibrium in both stoichiometric and non-stoichiometric elements or oxides, and in this module we have taken the oxide as MO. So after that we have taken all the conditions and calculated the reaction rate, and from the reaction rate we did the analysis about the dependence of the concentration on the partial pressure of oxygen. Thank you.